All right, welcome back. So now we're going to talk about an example of what they call an explosion. It says here an explosion uh, is where particles of the system they move apart from each other immediately or from each other after a brief intense interaction is the opposite of a collision. So an explosion is an opposite of a collision. Collision things they come together, an explosion they move apart. And the explosive forces which could be from an expanding spring or from expanding hot gases, as in like a bullet, are internal forces. If the system is isolated, its momentum or its total momentum before the explosion will be conserved. So, yes, the mechanical energy is not conserved because, for example, here in this next one, where we have a 10-gram bullet is fired from a 3-kilogram rifle with a speed of 500 meters per second, what is the recoil speed of the rifle? So you have a rifle and a bullet initially at rest, and then due to this expansion of gases, due to the chemical interactions, the bullet starts to move. And so you had zero mechanical energy at the beginning, and then you have mechanical energy that's definitely not zero because the bullet was not moving and now it is, and the rifle is also recoiling. And so, however, you cannot apply conservation of energy because there are non-conservative forces at play. But since those non-conservative forces are internal, then the momentum is conserved, and that's the key. So here is the example. You have your, sorry for my lack of drawing abilities. So here is the rifle, here is the bullet, and you will have the mass of the rifle, and this one will be the mass of the bullet. R for rifle, B for bullet. The initial momentum is equal to zero because nothing is moving. This is before what they call explosion. And then afterwards, here's your rifle, here's your bullet. The bullet is moving this way at some speed. The bullet, in our case, it's 500 meters per second. And the rifle is here, the mass of the rifle. It has to recoil back at speed of V rifle. Think about why it has to recoil back. The total momentum before was zero. The total momentum after has to also be zero. So, if the bullet is moving to the right, that's momentum to the right, and it's positive. The rifle has to go to the left in order to, when you add negative momentum plus positive momentum, they have to add up to zero. So the momentum afterwards, P final, will be the mass of the rifle times the velocity of the rifle plus the mass of the bullet times the velocity of the bullet. And we're going to say, first of all, there are no external forces on the system. The net external force is equal to zero, and therefore the rifle will recoil. You might say the person is holding it. Yes, that's an external force, but we're talking about before collision, right after collision. Yes, the person, imagine like you pull the trigger and nothing is holding, like the rifle is on a frictionless table, you pull the trigger, the bullet goes this way and the rifle would go that way. Now, of course, there is a person holding it. When the rifle recoils, the person is holding it, and so the person applies a force this way to stop the rifle from going too far. So we're not talking about that. We're just have in your mind a bullet and a rifle. The bullet goes to the right, the rifle goes to the left. So we're going to say the momentum before is equal to the momentum after. Momentum before collision is zero. The momentum after collision is mr vr for rifle plus mb vb. And therefore, v of the rifle will be negative the mass of the bullet, v bullet over v rifle. And it's negative because if the bullet is moving to the right, the rifle would move to the left. So I have negative, the mass of the bullet, it's 10 grams, so that's 0.01 kilograms. The speed of the bullet is 500, and then the rifle is 3 kilograms. So 3, and so V rifle would be negative 500, so it would be 5/3, that's 1.6 something, I think like 1.67, 1.7 meters per second. Okay, let me just double check my work. And it's always good to double check. Yeah, that's good. All right, let's go to another something that disintegrates. And so you have something at rest, and then it just disintegrates and goes into fragments, and we're going to see what happens. So here is an example of another thing that's initially at rest and then becomes into two fragments. One fragment will move in one direction, the other one will move in the opposite direction. So it says uranium-238 nucleus is radioactive. Okay. It disintegrates into a small fragment that is ejected with a measured speed of 1.5 times 10 to the 7 meters per second, and a daughter nucleus that recoils with a measured speed of 2.56 times 10 to the 5th meters per second. And then it says, what are the atomic masses of the ejected fragment and the daughter nucleus? So the atomic mass is, so for example, uranium-238 has an atomic mass of about 238 units. So basically 238 times the mass of the proton, pretty much. Because uranium-238 has 92 protons and 146 neutrons, and they essentially have the same mass, about 1.67, 1.66 times 10 to the minus 27 kilograms. So we're just going to say the total mass is 238 units, whatever that unit is. We don't really care. And then go from there. So here is I don't need these. Let me chop. So here is here a daughter. Here is an R here. So here is the mass here. The mass is 238 units. All right, that's the total mass. The initial momentum is equal to 0. P initial, it's not moving. You got the nucleus and it's just sitting there, and then it disintegrates. Disintegrates into some daughter nucleus. Let me call it the mass of the daughter nucleus, MD for daughter, that possibly could move this way at some speed of the V daughter nucleus. And then the small fragment, the mass of the fragment, and it will move this way at speed of the fragment. The speed of the fragment is 1.5 times 10 to the 7. And the speed of the daughter nucleus is 2.56 times 10 to the what power? The 5th meters per second. And they want to know what is this, what's this mass, and what's this mass. So how many units is it? Is it 20 units? Is it 50 U? And this one maybe is something. You know that their total mass has to be equal to this. So we want to know what their masses are. So we're going to say the momentum after P final will be, this one is moving to the left, so it's negative. The VD, the mass of the daughter nucleus, V daughter nucleus, plus the mass of the fragment, V of the fragment. Okay, I already put a minus sign here, so when we plug in VD, we're going to plug in positive 2.56 times 10 to the 5th. If I didn't want to put this and put the minus sign here, that's also fine. So just remember, don't plug in the minus sign only once, not twice. So I already took care of that, so at the end I'm going to plug in positive value. We're going to say, all right, no external forces, so the net momentum is, total momentum is conserved, so P initial equals to P final. P final is this, and it has to equal to this, so that's equal to 0. So let me write this and set it equal to 0. So you have the negative, the M daughter, V daughter is equal to M fragment, I'm sorry, plus m fragment v fragment equals to 0, and therefore the m daughter v daughter equals to m fragment v fragment. And so I'm going to divide by m fragment on both sides. I'm going to divide by vd on both sides to get a ratio. So I get the mass of the daughter nucleus divided by the mass of the fragment would be v of the fragment divided by v of the daughter nucleus. And let's see what we get, first of all. Let's see what we get, and then we will continue from there. V of the daughter. So v fragment is 1.5 times 10 to the 7. V daughter is 2.56 times 10 to the 5th or 4th. Let me double check in the book if it's 4th or 5th, and then go from there. I think it is to the 5th, so we're okay. Let me get my calculator then. Let's see. So I have 1.5 times 10 to the 7th power, and then I will divide by 2.56, and then divide by 10 to the 5th power, and that gives me about 58.59. So the mass of the daughter nucleus is 58.59 times heavier than the mass of the fragment. And so we just have to say then the mass of the daughter nucleus plus the mass of the fragment, both of them have to add up to the initial mass, which is 238 U. And so I will replace the mass of the daughter nucleus will be m fragment times 58.59. So this will be 58.59 the mass of the fragment, because the daughter is heavier, 58.59 heavier than the fragment, plus the mass of the fragment equals to 238 U, and so the mass of the fragment will be that. This would be 59.59, and so you get the mass of the fragment. So plus 1. Let's see here, to the 1 times 238. So I get the fragment has about a mass of 3.99 U, approximately 4 U. And then the mass of the daughter, so this is about 4, so the, what's left is 234 U. Okay, so that was that. And and so the fragment is apparently has 4 times is 4U. That's like a an alpha particle, like a helium nucleus. Okay, and so basically 2 things I have left in this chapter that I would like to talk about, which is conservation of momentum in 2 dimensions, collisions in 2 dimensions, and then the last segment is the rocket motion where the mass is changing. And that should put an end to this chapter. So, for conservation of momentum in 2 dimensions, so if the net force in the x direction is equal to 0, the net external force in the x direction is equal to 0, then the momentum in the x direction is equal to 0. And if the net external force in the y direction is equal to 0, then the momentum in the y direction is conserved. And if the net external force is equal to 0 period in both directions or in all directions, then the momentum in the x direction is conserved and the momentum in the y direction is conserved. So here's an example of a fancy example. You could consider them just any 2 masses, or if you like a real life example. Here is a 0.8 kilogram falcon bird is flying at 18 meters per second, swoops down at an angle of 45 degrees from behind a 0.36 kilogram pigeon. Why? Well, to hunt it. It preys on it. And so let's see what's going on. So here is the falcon. The mass of the falcon is going this way at 45 degrees below, like so. 45 degrees it comes toward this pigeon, and the pigeon is going like this. This is the mass of the pigeon bird, and going horizontal. V pigeon is 9 meters per second horizontally. So 9 meters per second. However, the falcon is moving at MF is moving at 18 meters per second. 18 meters per second. So it's moving faster in order to catch it. So they collide, it catches it, and then afterwards you will have the falcon here, and so you just have a total mass of MF plus MP, and they will be moving in a certain direction. They will be moving in a certain direction. And the question is, what is this velocity in the x direction after they stick together, and what's the velocity in the y direction after they stick together? And so they say, what are the speed and direction? Well, we're going to find the momentum in the y direction and then the momentum in the x direction, and then see what happens. So the momentum in the y direction will be the mass times the velocity in the y direction. So for the falcon, y of the falcon initial, all right, that's a lot of subscripts. The y component of momentum for the falcon initially will be the mass of the falcon, which is 18 kilograms, times the velocity of the falcon in the y direction. And the velocity of the falcon in the y direction will be 18 times the cosine of 45 degrees, but it's downward. So it would be, I'm sorry, what did I do? The mass is not 18, the mass is 0.8, sorry. The mass is 0.8 kilograms. The speed, V falcon, is 18. Yeah, okay. So this is 0.8, 0.8. 0.8, and then times 18 times it's this part of the velocity, so it'll be the sine of 45, and so 18 sine of 45 degrees. It's kind of squeezed, and it's negative because it's downward. So for the falcon, P falcon initial in the y direction will be this. So let me write it down. It would be what? 18 times the cosine of 45 degrees times 0.8, and that's negative 10.8. Negative 10.8, 10.18. And it's in units of momentum, so kilogram meters per second. And then for the P falcon initial in the x direction would be the mass of the falcon, which is 0.8, times the speed of the falcon, which is 18, but then times the cosine of 45. 45 degrees. 45 degrees. And if you do that, you get, well, sine and cosine are the same, but it's in the positive direction, so it would be 10.18. I meant to say sine and cosine of 45 degrees are the same. Okay, so that's for the falcon. Let's see. Go here. How about the pigeon? The momentum of the pigeon, initially in the x direction is the mass of the pigeon, which is 0.36 times the velocity of the pigeon. It's 9, but it's the velocity is in the x direction, so it's just that. It doesn't have any y component. So for the pigeon, pigeon initial in the y direction is simply 0. It doesn't have any momentum in the y direction. So 9 times 0.36, that's 3.24. kilogram meters per second. Okay. So let me just to be clear, let's write down the momentum, the initial momentum of the Falcon, P Falcon initial. It will be 10.18 units in the x direction and 10.18 in the negative y direction. So it will be 10.18 I hat minus 10.18 j hat, and then for the Pigeon, P Pigeon initial will be just 3.24 I hat. It does not have any j hat, it's equal to 0. So the total momentum initially, P initial therefore, would just be the sum of these two. So 10.18 plus 3.24 will be 13.42 I hat, and then minus 10.18 j hat. That's the total momentum at the beginning. And the total momentum at the beginning should equal to the total momentum at the end. Total momentum at the end will be the mass times the x velocity, the total mass, because they will be moving at one piece, as one piece. And so the total momentum at the end, P final at the end, will be the mass at the end. Their mass is the mass of the Falcon plus the mass of the Pigeon. That's 0.36 kilograms plus 0.8. That gives us 1.16, I guess. 0.36 plus 0.8, 1.16. So it will be 1.16 times their velocity in the x direction, I hat, and then plus 1.16 times the velocity in the y direction, j hat, right? Momentum in the x direction is the mass times the velocity in the x direction, and the momentum in the y direction is the mass times the velocity, the component of velocity in the y direction, j hat. And these have to be equal. So this has to equal to this, and this has to equal to that. They have to be equal. So matching them, let's match them. This will give us Vx will be 13.42 over 1.16, 13.42 over 1.16, and that's 11.57 meters per second. And then in the y direction, well, these have to match. Vy equal to 10.18 over 1.16, 10.18 over 1.16, but it's negative. Negative 8.776. Negative 8.776 meters per second. That's that. So what's their speed? I think they say what's their speed? The speed will just be the x component squared plus the y component squared, square root. So the speed will just be Vx squared plus Vy squared, square root. When you do that, you will get 8.776, and you square it, it becomes positive, of course. And then plus the 11.57, you square it. Then you take the square root. I get a speed of 14.52 meters per second. And then what's the angle? Well, here is it has this component of speed in the x and this component of speed in the y direction. And it's more in the x. It's a little bit, the speed is 8 units in the y and about 12 units or 11 units in the x. So it looks like this. So the direction is this way. You want to know this angle here, theta. So we'll just do the y over the x, get the tangent, but remember the angle is below the x-axis, so it will be negative. So it will be arc tangent, tangent inverse. Let's clear tangent inverse of 8.776 over 11.57. I just plug in positives and then I know my angle is 37.18 degrees, but it's below the x-axis, so the angle is 37 point, about 2 degrees below the x-axis, so that's negative. And let me just double check my work. And yeah, about 37 degrees. And the speed is, yeah, so we got it, 11.6, and they have 8.78. Yeah, so sounds good. Okay. I was just concerned I made a mistake or something, but it's always good to double check. Before I get to the rocket equation, I have one more problem that I wanted to talk about, which is like a projectile that then explodes, becomes into basically 3 fragments. But I think I have about 6 minutes left in this video, so I will pause this and then start it in the next video. I think it's better, and then we will continue.